Hi friends, Mrs. McBride here. Shout out to Megan Grierson trying to use a pen today. We'll see how this goes. But first thing I want to do is a quick joke. What did the orange say when it was stepped on? You hurt my peelings. All right. So today we're talking about the electric field. And before we talk about the electric field, I want to do a quick review of what is the gravitational field, because everybody loves a good field. Am I right? You might be thinking, what the hell is a field? And what a field is an invisible force field where forces are acting on an object without touching. So for example, quick refresher. Here's Earth. And if I take a ball, obviously this is not drawn to scale, and I throw it up in the air, well, what's it going to do? Well, it's going to come back down to Earth due to gravity, okay? And if I put a ball over here, we would find that it would also come back down to Earth due to gravity. And the same thing would be true if we were on the South Pole. Over here on the equator, I don't know why the ball all of a sudden shrunk sizes. Let's make it the same size. But either way, we could draw this field, which just basically says that anytime something comes away from Earth, it's going to come back towards it. Well, it turns out that the same thing is true with charges. So for example, let me just move my setup here. Let's say, for example, I had a positive charge here. Well, what if I brought a negative charge close to it? Well, it would move towards it. Or if I brought a negative charge over here, well, it would also move towards it. Okay? Do you see how this is the same sort of scenario as the way we know how the gravitational field works, is how the electric field is going to work. Okay? So what's the definition of an electric field? An electric field is created in the space surrounding a charged particle. So that's kind of like what it is. It's created in the space surrounding a charged particle. Okay, and to be more specific, or to give you a more physics definition here, we could say that it relates the force exerted to the size of the test charge. Okay, so this is what it means. It means that an electric field is created in the space surrounding a charged particle. It's this invisible force field that tells us what direction a charged particle will move when it gets closer to another one. Okay, the equation relates the force exerted to the size of the test charge, and we'll get to that in just a second. What do you think would be a good symbol for the electric field? Hopefully you said capital E, and you would be correct. Okay, we'll skip the units for a second and we'll talk about the equation. So the equation relates the force to the size of the test charge. So we can write the equation that the electric field is equal to the electric force, there's our friend Fe from the last video, divided by the test charge. Hopefully you're reminding yourself that charge is Q. Okay, an electric field just has the same units as these things. So force is measured in newtons and charge is measured in coulombs. So the units of the electric field are newtons per coulomb. Pause this video for a second if you haven't already taken out your green sheet, or if you were like me and knew this was coming, write this on your green sheet, that E is equal to Fe over Q, okay? And I would just remind you that E is the electric field, which is measured in newtons per coulomb, okay? a couple quick notes here. An electric field is created in the space around a charged particle or configuration of charges. If a charged particle is placed in an electric field created by other charges, it will experience a force as a result of the field. We can easily calculate the electric force from the electric field or vice versa. So if you're given the electric field, you can find the force, or if you're given the force, you can find the field. Okay? Remember, force is measured in newtons. That's like an actual push or pull. A field or a force field is the invisible space surrounding a charged particle. Okay, flip the page here for a second, friends. Are you ready for some drawings? Okay, this is just saying that what would a field look like around a positive charge? Well, if we had a positive particle here, okay, and we wanted to draw in the force field, the way I try to remember this is it's as though we're putting a tiny little positive charge here. This is our test charge, okay? And if we put a positive near another positive, what is it going to want to do? Hopefully you're saying repelling, okay? And if we put a little positive over here, it's going to want to repel. Or hopefully you're following the pattern and you can see this nice picture of what the force field looks like. Now, I always draw mine with 8 arrows. The number of arrows that it has tells you the strength. The more arrows, the stronger it is. I always draw them with 8 arrows just because that's the way I do. So I would recommend you drawing them that way. But just know that if you see a picture and it has a fewer amount of arrows compared to more arrows, that would be the stronger one. I'll give you a couple examples down below, okay? What does a negative charge look like? Well, you can imagine if I put my same positive test charge, why is the test charge positive? Well, that's just the convention that we use as physicists. We could have used negative, but this is just what we use, okay? What would happen to this particle if it sees this big negative? Ooh, it would be attracted, okay? And if we put our positive friend over here, it would also be attracted, okay? So you can see how you can figure out whether something is positive or negative by looking at its field, okay? I always think of like this: positive people radiate out and negative people keep it all in. I don't know how you want to think of it, but that's the way I think. All right, let's get crazy here. What happens if you had a positive and a negative in the same vicinity? Whoa, okay? Well, this guy would be radiating out because he's positive. This negative guy would be keeping it all in. And what you find is that this guy is starting to be going out this way, and he's like, no, 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 I'm attracted to you. Same thing over here. Whoa, I'm attracted to you too. Okay, so you get this kind of shape here that looks sort of like this. When I was a high school physics student, I always used to think these look like spiders a little bit. Okay. What happens if you had 2 positives? All right. Well, this guy's starting to come out, right? And then he's like, whoop, I don't like you. Your, opposites are attracting, but in this case, we've got likes repelling. This guy's starting to come out, whoop, I don't like you. Okay, so we get a shape that looks, this is where I think they start to look like spiders. Now you see what's going on here? That's a very special spot, okay? And the cool thing about this, and we can actually see this happening, is that at this exact spot here, the electric field is equal to 0, which is pretty neat. There's nothing going on here. All right, if you liked that picture, you're gonna love this picture because this one is sort of the same, but what would be different? Okay, so the arrows would be in the same shape, but pointing in the opposite direction, right? Hopefully you are enjoying drawing these as much as I am. Draw your little electric field spiders. And then the same thing here. We also have that the electric field is zero there. All right, I want to draw some stuff down here at the bottom, so save some space. Kind of tuck this one in nice and tight up here. Sometimes you see it like this, where we have two charged plates. We're going to talk about capacitors later in this unit, and a capacitor is two charged plates on top of each other. Capacitors are what stores charge or makes rechargeable batteries. Okay, so if you had two charged plates, you'd see the same sort of thing, that the positive was always going to the negative, except on the ends where you get this whoop, whoop. All right, so what kinds of things would I expect you to know? Well, I would expect you to know, first of all, what if I drew you a picture that looks like this? And you don't have to draw these. This is just my okay. So let's say this is A, and this is B, and this is C. Okay. First of all, can you tell what charge A is? Hopefully you said to yourself, A, the arrows are coming in, A must be negative. Can you tell what charge B is? Well, hopefully you said, well, if I look at the arrows are going out, so B must be positive. And if I look at C, C's got the arrows going in, so that again must be negative. Then I could ask you, well, which one of these, A, B, or C, is the strongest charge? And hopefully you would say, well, it must be B, because B has 1, 2, 3, 4, 5, 6 lines coming out of it, but A and C only have 3 lines. So that must tell you that B, not only is B positive, but B is also the strongest one. Okay, and I want to give you a quick note for your homework, which is due on Friday, that we have this equation E equals FE over Q. And what you'll find a lot, I would say in like, I don't know, 90% of the problems that you do, they'll tell you that this is either an electron or a proton. And you have to remember that if they tell you that this is an electron or a proton, that electrons and protons both have the elementary charge, right? Or 1.6 e to the negative 19 coulombs. So just be careful about that, all right? Next time I'm on the video with you, which will be on Monday, we're going to do the rest of this and sort of finish off our electrostatics unit. Megan, I hope this pen did its job and you can clearly read everything that I am drawing. See you guys soon. Have a good day. Miss you guys. Bye.